Okay, so I'm hoping that everyone can hear me now. So welcome to the second lecture of the day. And the topic is going to be a more GPU programming basics. And the level is going to be something that I consider to be between basic and intermediate. So first thing I have to mention is the compute capability. So different GPUs can have a very different architecture in them, and they can also have different kind of capabilities. For example, some older GPUs do not have the tensor cores, and some newer higher NVIDIA GPUs have the tensor cores. So if you are writing code to these GPUs, you must know on what type of GPU you are working on at the moment. And NVIDIA uses something called compute capability to enumerate the capabilities and architecture of the GPU. And the number is made of two parts. There is the major part that is usually refers to the architecture itself, and then this minor part that tells you if it's the same architecture, it could be a different kind of chip running on, and it could still be slightly different. There could still be a difference between GPUs that are on face of it based on the same architecture. And right now, the relevance are pretty much 3.x, which is going to be a Kepler architecture. So if you buy a gaming card, it's going to be GTX 700 series. Or if you use a computing-oriented card, it's going to Tesla K80s that can be also found from the Kepler machine. If it's 5.x, then you're dealing with the maximal architecture, and that is mainly the GTX 900 series. 6x is going to be Pascal, so GTX 1000 series. 7.x is a Volta architecture, so it's this Tesla V100 that you're working on during the handstones. Then we have 7.5 that is actually a different architecture called Turing, and this is mainly RTX 2000 series. And then we have 8.x that is Ampere architecture, the most latest one. That is RTX 3000, so a minor typo here is supposed to be 3000. And then the latest and greatest Tesla A100 GPU is also of this architecture. During this course, since we have access to these V100s, I'm mainly concentrating on 7.0 Volta, but I won't be talking about any kind of fancy optimizations that only apply to the compute capability 7.0. So most of the I'm mainly talking about best practices in the sense. Then you should also consider that every new CUDA version, so there is this compute capability that refers to the GPUs themselves, but CUDA itself has several versions, and each version has introduced new functionality. And some older GPUs do not necessarily support all of the functionality that's implemented in the latest version of CUDA. And sometimes you may even a situation where you have to write a piece of code that is going to do compile check which compile capability you are compiling on, and then write a slightly different version of the code that takes account the differences between the different architectures. So let's take a little recap for about the previous lecture. So I told you that we have a host with the CPU and RAM. We have the device being the GPU. Inside the GPU, we have streaming multiprocessors, and inside a streaming multiprocessor, you have a set of CUDA cores. And then the threads are, we have this large pool of threads that are divided into thread blocks, and each thread block is mapped to a single SMP. And each SMP can have multiple thread blocks mapped to it. So there is no reason to be one-to-one mapping. It's usually beneficial to actually have several thread blocks running on an individual SMP. And then there is this thing called simultaneous hardware multithreading. Again, you have multiple threads per core. And it's just a scheduler that is always going to maintain the pool of threads from which it's going to select a thread that is ready to execute. But that was a little bit of simplification, because if you actually look at the V100 GPU and look what is how the SMP looks like, you will get something like this. So you actually have these smaller units where you have a scheduler, you have registers, you have cores here, and then you have shared memory and L1 cache here that is shared among all these subunits that we have discovered here. And each one of these subunits, 4 of them in this example, is called processing block. And inside each processing block, you will have the following. You have a large set of CUDA cores, and there is usually separate cores for doing integer operations. and for 32-bit floating point, 64-bit floating point. Reduced precisions, you have the tensor cores, and then you also have special function cores that can do like trigonometric functions. Then inside each processing block, there was one scheduler that is going to select the threads to execute and issue the instructions to some of these cores. And then we had the register file that was a large pool of registers that is shared among all the threads that are executing on the processing block. The shared memory and the L1 cache are being shared between all processing blocks. So that is a common resource to all threads that are being executed on SMP. What I left out on the figure were, for example, dispatch units, L1, L0, L1 instruction caches, load and store unit and texture units, and that kind of stuff that simply made this figure here way too cluttered. If you want to find more detailed information, there is a white paper from NVIDIA about the V100 architecture that has more detailed illustrations how the SMPs looks like. So if we now go and compare this figure here to the typical CPU, where you might have, let's say, 4 cores, and each core will have its own scheduler, its own register, its own L1, L2 caches, and it's only the L3 that is being shared among the cores. There are these units that kind of resemble cores. They are the execution ports that actually execute the instructions, but no one usually refers to these execution ports as cores. It's considered that the scheduler, the register, and the caches and execution ports together form a core. And compared to this what happens in a GPU, you would imagine that each one of these processing blocks should be called a core. But in NVIDIA terminology, each one of these smaller units here is a CUDA core. So in general, GPUs allocate more silicon space to do the units that do computation, and less silicon to the units that direct the computation. For example, the schedulers and the dispatch units. And this means that you can get way more computing power on the same size of die. And it's also modular because you can simply scale up the number of SMPs to get more cores. You can add more processing blocks inside the SMPs, and you can have more cores inside the processing blocks. So it is much easier to scale up to thousands of cores. However, these cores CUDA cores share a lot of resources, which means that some people could argue that they are not really true cores, and should we actually call them execution ports? And of course, the fact that they share a set of cores, share a scheduler, that is going to be quite a significant complication when you're writing a code. And the first complication that happens is that the thread blocks are actually subdivided into even smaller units called warps. And within each warp, there is going to be 32 sequentially numbered threads. And this is why in the previous lecture I mentioned that the thread block size should be a multiple of 32. That is because the thread block is divided into warps. And then on a hardware-wise, what is meant by that the 32 sequentially numbered threads is that the hardware will have one-dimensional indexing for the threads, starting with the X dimension, and then going through the Y dimension, and then going through the Z dimension. And in actuality, in most cases, if two threads have adjacent thread indices in the X dimension, then they are very likely to be in the same warp. And in the illustration, you can see that if you compute the global index numbers for each thread from 0 to 31, it's going to be warp number 0. From 32 to 63, it's going to warp number 1, and so on and so on. And when you launch a kernel, it's going to generate this set of warps, and the warps are then going to distribute it among the processing blocks. And in case of the V100, the Volt architecture, this distribution is done statically. So at the beginning, for each warp, it is selected, processing block is selected to it. Every time the scheduler is ready to issue an instruction, it is going to select one warp. So not one thread is going to select an entire warp and execute an instruction for it, and select an instruction for it, and then issue it to a set of CUDA cores. And then the number of instructions that will be issued in a given cycle depends on the architecture. There are, for example, With a Kepler, you could have 2 instructions issued during each cycle. With the Volta architecture, you can have 1 instruction issued during each cycle. And the key thing to understand is that since it's not the thread base, the scheduling is not done thread basis, it's done on the warp basis. Then all the threads within the warp will actually execute exactly the same instruction. And those threads that don't have anything to do will be simply disabled automatically. So if you imagine a simple piece of code where we have some printf statements, for the first one, it is going to all threads in a warp, all 32 of them will execute this printf statement. But then we have the if statement block here. We are going to take only the threads whose thread index is more than 16. Now we will have only half of the warps will go and execute this printf function here. And in the next one, we are going to filter out even more threads. And then in the else statement, we have only the remaining threads executing. Yes, question?
Yes, there is a question. Is that 32 common for all GPUs?
It is common to all NVIDIA GPUs. If I remember correctly, at least a couple of years back for AMD, it was 64 threads in the same. But NVIDIA, it has been 32 since the first GPUs that supported CUDA. Okay, but when you actually run this code, it will behave as if it was individual threads running it. It is just that on a hardware level, it will all the threads in the warp will go through all these instructions, and some of them are simply disabled in a manner that the final result is never being stored anywhere. But the thing is that even though the threads are disabled, the overall cost of executing this kind of piece of divergent code is almost the same as if all the threads would have executed all the necessary instructions. So you end up being, if you have a code where you have a if or if else block that splits the warp, then you will lose some of the performance. What should be pointed out that even though all the threads in a warp execute the same instruction, it doesn't actually trigger memory transfers and that kind of stuff. It simply means that a certain number of cores will be idle. So if we imagine that we have one warp that is now being mapped to this one processing block here, and then we have this half of the thread warp, this 1/4 of the warp is going to now issue a double precision instruction. And in that case, they will end up going all these double precision cores. And the second instance is this first half warp is going to be such a way that only the first half of the half warp is active, and the second one is inactive. It is still going to use all the single precision cores, and half of them are going to be idle during this cycle. And the same thing happens if you would do something like you had a situation where second half warp happens to be idle completely. Then during this instruction issuing cycle, all the single precision cores will be idle. They are doing nothing. And this can actually become a bigger problem than could be expected, because if you assume that a single thread has a probability of P of diverging or being disabled in some part of the code, then the probability that at least one thread in the warp will diverge is going to be given by 1 minus P to the 32th power. And then when you look at that, if you have only 20% probability that individual thread in the warp will diverge, it's really was 100% guaranteed that the entire warp will end up diverging. So even if you have some very rare situation where you end up having diverging execution paths for the threads of the warp, it can still get quite costly. Now then to the next topic, which is synchronization. It is quite often necessary to synchronize the threads. For example, we want to be sure that certain memory operations has been finished before we start using the data for something else. And simplest way of one of the simplest ways of doing synchronization is to create a barrier. And all threads are supposed to encounter the barrier, and all threads will wait at the barrier until all threads have actually encountered the barrier. So in this example, we would have 4 threads that individually start encountering the barrier. And every time they encounter it, and if there are still threads that haven't done it, they will just wait until the last thread encounters the barrier. And after the barrier, all threads are free to move on with their execution. And there are several ways to implement a barrier in CUDA. First one is globally, meaning that we want to synchronize all threads in all thread blocks using a barrier. And the easiest way to do is that you will simply implement the separate kernels, because all the threads are created at the beginning of the kernel, and we will guarantee that all the threads have finished by the end of the kernel. So in that way, we can have a global synchronization by simply cutting the code into multiple kernels. Then if you want to be sure that it's the host thread that is being synchronized, then you can use the CUDA device synchronize function. And what this will do is that when the host thread is calling CUDA device synchronize and we still have a kernel running, it will simply force the host thread to pause until the last remaining thread has finished executing the kernel and the stream becomes empty. And after this point, the host thread is allowed to continue and do what I was doing earlier. Then if you go inside the kernel, there you can actually synchronize threads that belong to the same thread block. And this is done with a function called sync threads. And in this illustration, you have two threads blocks, and they will start encountering the barrier. And then finally, once the last thread in this thread block encounters the barrier, then all the threads are being released and they can continue with their execution. And the same happens with the second thread block. But the key thing to realize is that these barriers are completely independent between the two thread blocks. So it is only those threads that belong to the same thread block that will be affected by the sync threads function. Then last thing that I will just briefly mention is that in the newer version of CUDA, it is also possible to synchronize all threads that belong to the same warp. And on the face of it, this might sound a bit weird because I say that all the threads in a warp execute together. But with the newer versions of GPUs, such as Volta and newer versions of CUDA, there is something called independent thread scheduling. And in those cases, this instruction can actually become useful. But I'm only mentioning it because this instruction has started appearing in all sorts of tutorials, and it's not actually that useful with the older GPUs that are older than Volta. So if you find the tutorial that uses sync warp instruction, you should first go and read about independent thread scheduling before you use it in your code, because it can actually behave in a weird way on pre-Volta GPUs. The next topic is going to be a global memory. So this couple of gigabytes of memory that exists on the GPU. And one of the key factors that influence the performance you will have this memory is the L1 and L2 caches. So the cache line size for the global memory is 128 bytes, or 32 floats or 16 doubles, and each cache line maps to a line segment of the global memory. With many GPUs, you can go and disable the L1 cache, in which case the cache line will become 32 bytes. So if you're a situation where you are accessing the memory in more random pattern, then it might make sense to actually go and disable the L1 cache. So in this illustration, you can see that you have memory addresses running from 0 all the way to 127 here, and this is going to be one 128 byte cache line. And then from 128 all the way to 255, we have the second cache line, and so on and so on. And the key thing is that the warps, all the threads that belong to a warp execute instructions together, and they therefore access the memory. And when one thread in a warp is going to access the memory location, it is going to cause the memory controller to fetch the entire cache line, which can lead to problems. For example, here you can see that we have these 4 threads active, and they will end up accessing the memory in very random pattern, and therefore it is going to load all 3 cache lines to the cache, which is of course not necessarily that efficient if it turns out that you just need this one byte here, and this byte here, and this byte and this byte here. You are doing way more, you're fetching way more from the memory than what you would actually need. So for optimal performance, each warp should access adjacent memory locations that span across as few cache lines as possible. So it doesn't have to be like each thread is accessing neighboring threads are accessing neighboring memory location. It's just that when you consider the entire warp, then you should access adjacent memory locations and try to make it so that the memory access fall to as few memory pages as possible. In this instance, we have quite optimal memory access pattern. We must the first half of the warp is going to only access memory that is on this memory page, memory cache line. I'm sorry, I got distracted normally. When I said earlier about memory page, I meant the cache line. And the second half of the warp is going to access this cache line here. And now going through a couple of memory access patterns where I'm actually comparing how a memory access pattern will perform on a CPU and then compare to the GPU. So first, I have this very simple access pattern where I have a for loop on a CPU, and it's parallelized with the OpenMP parallel for, such that it's statically, this for loop is cut into segments where each segment is 64 iterations, and each one of these 64 segments is assigned to a different thread. So what it will look in practice is that the first thread would start accessing here, and second thread would start accessing here. And as long as the memory in as long as this X vector is aligned in suitable manner, then each thread will start accessing a different cache line. And this usually leads to reasonable performance because there is no competition between these two threads. They are accessing completely different cache lines. Then if you would change the loop in such a way that you make the batch size to be only 1. So the first thread is going to start from 1, 0, second one is going to start from 1, and so on and so on. Now you have a situation where the threads would actually go and access the same cache line. And this would lead to false sharing, which will affect the performance very negatively. So good on a CPU, you make sure that the different threads access memory that is reasonably far from each other. And in a bad case, you will make the thread access memory locations that are very near to each other. But then when you move to a GPU, you will actually have a completely separate situation. So let's first look at the access pattern where two threads that have the neighboring index numbers are actually accessing memory locations that are near to each other. And whereas on a CPU, this would lead to horrible performance. We must remember that the whole warp is going to access the memory together. And therefore, the first half of warp will actually go and access this cache line together and actually give a very good performance. And the second half of the warp will go and access the second cache line and thus also give very good performance in the GPU. And then if you would take a different kind of access pattern where each thread would start from a different location on the buffer and then just access adjacent memory locations. And this would have been really good on the CPU, but on a GPU, you will see that now you will actually end up spanning the memory accesses across the very wide area. And during each cycle, each warp is going to use just one of these memory locations from each cache line. So this will usually lead to very poor performance on a GPU. And it just turns out to be that the memory access pattern that is very optimal for a CPU ends up being unoptimal for a GPU and vice versa. Then a couple of words about the shared memory. So in the earlier illustration, I showed you that all the processing blocks inside SMP share this shared memory / L1 cache. And in Volta, it is total 28 kilobytes, and it is being shared between the shared memory and L1 cache. And when you have a thread block being scheduled to SMP, the kernel is allowed to take a section of the shared memory and use it to the computations done by the thread block. Shared memory is significantly faster than the global memory because it actually exists on the die itself, and it is physically located very close to the cores. The downside is that the memory is actually divided into 32 memory banks, and successive 4-byte words will map to successive banks on a Volta architecture. So in this illustration, you can see, again, we have memory addresses here, and every time we have 4 bytes, those will belong to the same bank. So these memory locations here belong to bank number 0, and these memory locations here would belong to bank number 22. And each bank has the memory bandwidth of 4 bytes per cycle. And if 2 threads end up simultaneously accessing the same bank, then it will cause a so-called bank conflict. And the 2 memory transfers must be done sequentially. The only exception is that when the 2 threads are actually accessing the same memory location, then the GPU will do a broadcast operation. Otherwise, if one thread accesses this location and other threads access this location within the same warp simultaneously, then you will have a bank conflict. And let's again take a couple of examples. In the first example, we can see that all the threads are just accessing the shared memory more or less randomly, but for each bank, we will have only one access during the cycle. And in this case, we don't have any bank conflicts, and we therefore get optimal performance. But if we change this slightly so that now several threads end up accessing the same bank, now in this instance, we will actually have a 2-way bank conflict, and we will actually do 2 separate transfers. And we will effectively end up cutting the memory bandwidth half. There are 2 ways of allocating shared memory. The first way is that you do statically. So in the beginning, somewhere in the kernel, you declare that you have an array, in this case, an array of 256 integers, and you use the keyword shared in front of it, thus telling the CUDA compiler that this is meant to be in shared memory. Or you can do it dynamically, where you add the additional external keyword in front of it. And then it is going to be when you launch the kernel where you have to specify how much shared memory you want. And in this case, it is going to be the 3rd argument inside these brackets, where you have to specify how many bytes of shared memory you want to allocate for each thread block. So remember, this shared memory is shared among the threads that belong to the same thread block. If you have 2 threads that are different thread blocks, they will actually have a different array X. They cannot access each other's shared memory. And the typical way of using shared memory is that at some point during the computations, all the threads that are in the same thread block have to go and communicate some information. And I've taken this very simple transpose operation where we are given a 2-dimensional array and we want to swap the rows and columns. We want to do a transpose operation. And one way of doing the shared memory is that we will allocate 32 times 32 2-dimensional array from the shared memory. Then each thread is going to load the corresponding element from the global memory and store it into its own element in the shared memory. Then they are going to synchronize. So after synchronization, all the threads are sure that all the other threads in the thread block have executed the previous line here. And then they can go and read the data from the shared memory and store it back to their corresponding place in the global memory. So that is a typical, you allocate shared memory, then you do something with the shared memory, you synchronize, and then you do something with the data you have to stored to the global memory. But this is actually a very nice example to show you an optimal access pattern to the shared memory. Because when you look at this second access, where we are actually reading from the shared memory, we note that since the warps, it is the X dimension, in this case, that is going to decide which threads belong to the same warp. It means now that the first thread is going to access memory location here. And then the second thread in the warp is going to jump over the leading dimension of the array. So it's going to jump forward 32 at 32 elements in the array. So it is going to be end up accessing the same memory bank. And the same next thread in the same warp is again going to jump forward 32 banks. And it's going to be end up accessing exactly the same memory bank. So what you will actually get in this situation is a 32-way bank conflict. And the performance, it's going to mean that there's going to be 32 sequential accesses to the shared memory. But if you would go and modify this code a little bit, so change the leading dimension so that it's actually 32. And what would happen now is that the first thread in the warp would start, let's say, here. And the second thread within the warp would jump forward 33 elements in this array. So it is going to jump 32, and then it's going to jump to the next bank, and so on and so on. So with this simple modification, you would actually turn a 32-way memory bank conflict into a completely bank conflict-free situation. Then a couple of words about matrices. So there are, if you use the CUDA-malloc, or there is also a second command that I will talk about tomorrow, which is called CUDA-malloc aligned, they will actually align the memory to 256 bytes or two 128 byte cache lines. And this works really well when you're dealing with vectors, because then you can be sure that all the memory is aligned in a suitable way. But with matrices, which are two-dimensional arrays, we must make sure that each column in the matrix is also aligned. This is assuming that you are storing the matrix in a column matrix order. So meaning that you will start storing the first column like this and then jump to the next column and so on and so on. So if you don't do the alignment and then look how these columns will end up spawning across the cache lines, you will note that if you start accessing this column here, and then the first 16 elements here would actually spawn across two cache lines. Instead, what you should do, you should align it, making sure that the leading dimension of the matrix is always a multiple of the cache line length. And in this way, the first element in each column ends up being at the beginning of a cache line, and therefore you will get a much more optimal memory access pattern. There are two ways of doing this alignment. First one is that you do it manually, so you will keep using the CUDA-malloc. It is just that when you calculate the leading dimension, so meaning how many elements, how many words are being allocated for each column, then you just make sure that it is a multiple of that the leading dimension times the word size is a multiple of 256. But you could do the same thing also using something called CUDA-malloc pitch function. And this function is meant to allocate two-dimensional arrays. And the pitch here, so what it will return you the pointer that points to the allocated memory area. But it's also going to return you something called pitch. And the pitch is going to tell you the leading dimension, that has how many bytes have been allocated to each column. And then, yes. But the key thing to understand here is that because this is a C function, it assumes that you are actually storing the matrices in a row matrix format. So if you want to use the column matrix format that is more common with linear algebra codes, then you must actually go and swap the width and the height with each other. And remember that the width and both the bits and width are actually given in bytes. So, and then if you want to go and okay, maybe it's better to do with example. So if you actually want to allocate a matrix A with leading dimension LDA, then you should call the CUDA-malloc and get the corresponding pointer out of it, and then also capture the pitch, which tells you how many bytes are allocated for each column. And then you have to go and calculate the actual leading dimension by dividing the pitch with the number of bytes there exist in each word. There also exists a separate function that allows you to move two-dimensional arrays very easily. And again, you must remember that when you're given the pitch, that is going to be leading dimension in bytes. It is not leading dimension in the number of words you are using. You have to convert the leading dimension like done here. And then again, the width and height, they are swapped if you're using column matrix form, if you're storing the matrix in a column matrix format. And then both the source and the destination can have a different leading dimension. And here I have an example how it's been used. If you're assuming that the matrix A is stored in the host memory with the leading dimension LDA, and this time the leading dimension is measured in the terms of words. And then we have a second matrix that is going to be in the device memory called DA with the leading dimension DL/DA. Then you could do the memory transfer with the CUDA-menkopu by telling that the transfer is going to be from the host memory to the device memory, and then you're going to specify how many columns you will be moving, how many rows you'll be moving. So you have to multiply the LDA with the word size. And I'm sorry, I got a bit distracted here. Okay, so you specify the direction of the transfer, then you specify how many columns you want to move, and then you specify how many rows you want to move. And because this number of rows is given as a number of bytes, you have to multiply the number of rows with the number of bytes in a word. So you have to do m times size of tuple in this case. Then you will specify the source, so you give the source pointer, and then you have to specify the leading dimension of the source matrix in terms of bytes. So again, you have to multiply the LDA with the size of tuple, and the same thing in the destination. You give the destination pointer in device memory, and then you have to multiply the leading dimension with the word size. So the main thing that caused me a little bit confusion here for myself is that the pitch and the width, they are always given and returned in terms of bytes. And what is done for the height, that is comes with a number of elements. And this function assumes that you are storing the matrix in a row matrix format, and in actuality, in many codes, you're doing the column matrix format. So you have to remember to swap the height and width with each other, and then remember that these argument pitch and width, they are stored in the terms of number of bytes instead of number of words, which can sometimes lead to very interesting bugs because there is two kind of conflicts. One is that one of the dimensions given in terms of bytes, and then you swap the ordering of the columns and rows. So then I'm coming to actual handstones. So again, handstones same place. Under handstones 2-point intermediate, you will find two handstones called 1-point sum and 2-point. Yes, we have a question.
Can you explain matrices slides with a small numerical example?
Yes, let's see. Can I note? Yes, let's undo that. So in C, Birgitta, could you mute your microphone? Yeah, in C, the way you would usually store matrices is that you would store each row continuously in the memory. And this is just a convention with the C codes in general. And in this case, the width would be here. And that is given in terms of bytes. And here we have the height, which is the number of rows in the shared terminology. Okay, this is just wonderful. And that is given with the number of elements. And if you then go and look at how things are usually done in Fortran in many numerical codes, what you're actually doing, you are storing each column continuously in the memory. And in this case, the width you would actually give here, it is going to be this dimension here. So this is going to be the width you would give to these two functions. And this would be the height you are giving to the function. And again, this is given in terms of a byte, so you have to multiply it with the size of tuple. Would was that be a sufficient answer, or should I? Is there any? Okay, well, the main thing is that there is different conventions between C, where we store each row continuous memory. In Fortran, in numerical codes, you do it column-wise, so you have to remember to swap the width and height arguments. And then the width argument and the pitch argument, they are given in terms of bytes, and then the height is given in terms of the elements. And you should look at this example here. So I'm taking the pitch separately out of it, and I'm multiplying the m, that is the number of rows, with the size of the word, so size of tuple, and then I'm giving the n, that is now the number of columns in the matrix as it is. And then I'm converting this pitch into the actual leading dimension by dividing it with the size of tuple. Can you people still see the stuff I have drawn to the screen? Okay, now it's clear. Yeah, I should probably do better. There seems to be a question in Q&A.
Can you wait? Wrong. It was just thanks.
Okay, I'm sorry that I got even distracted by myself here, but it's a very you have two things working against you. One is that you're swapped the width and height of the matrix, and then NVIDIA decided that the pitch and the width are given in terms of bytes instead of elements. But when you're doing the handstones, you can come back to this slide here, where you can actually see how you can do the allocation and convert the linear dimension correctly. So going back to the handstones, I have two of them. First one is called one sum, and this is simply a code where you learn how to use shared memory and synchronize stuff. And the overall idea is that you will sum together the elements of the vector. And in the second one, we will learn again, keep learning how to use shared memory, how to synchronize, and also handle matrices. So this is the kind of tricky part here. And the goal here is that you will write a piece of code that performs a matrix vector multiplication. And as before, the model solutions can be found under solutions/2-point intermediate. And if there are no other questions at the moment, I'm stopping to share the screen and also stopping